totally open-ended, ask anything you want, even if you think it's maybe tangentially related. It's the 173rd event. This group has been going for 9 years. And today we're just doing one talk. We really wanted to do a deep dive into DeepSeek. So we did DeepSeek R1 a couple months ago, and DeepSeek R1 really was built off of a lot of the work that they did in 2024 with DeepSeek v3. There was a recent update on DeepSeek v3, but this paper, it is from last year. So with no further ado, we will invite Joe here.
Cool. All right. So, yeah, this talk is on is it automatically going? Oh, let's stop that. All right. This talk is on DeepSeek. It's pretty interesting because the news out of the other side of the pond got very interesting last year with like pretty good models. Not talking about Europe though, because they're not doing very much. But DeepSeek in particular, I would say, is the most interesting Chinese company, and so I've been looking into them a lot. Like Rakshak said, we did R1 not long ago. He did R1, and it was very impressive, and that's kind of what set the market into a spiral. But I would argue that it was largely because of the work done with V3 that everybody kind of freaked out, and the efficiency gains that we see in this paper. So DeepSeek was started in mid-2023. A little background on them. They're owned by a hedge fund in China called High Flyer. That was the joke. Everybody thought that hedge fund shorted NVIDIA before they came out with R1. We still don't know if they did. And then since mid-2023, they've been very busy. So they did DeepSeek Coder, DeepSeek LLM, DeepSeekMoE, Math, V2, V3, R1, all in like a 1.5 year period. And just sort of to get up to V3, we want to go through a bit of the background models that built up to this. So they basically started out with standard llama. They did a 7 and a 67 billion variant. It was trained on Common Crawl, standard 2 trillion token data set. It outperformed Llama 2, but it wasn't really all that much to write home about compared to closed models. And then they did a chat variant with supervised fine-tuning and direct policy optimization. Didn't make too much news though, because again, the performance wasn't that stellar. But then they went and they did DeepSeekMoE, and here's where we kind of start to see the major architectural innovations here. So they looked at MoE, at Mixture of Experts, and they realized the main shortcomings with Mixture of Experts were there's redundancy in the experts, meaning the experts learn a lot of the same information. They have something called expert collapse, where certain experts always get routed to and other experts never get routed to. And so they built a few things into here to prevent that. They basically did a lot more experts than normal. They had, I don't remember how many, but they had quite a few experts in this one. And then they had these always-on experts that were basically always routed to, plus the normal experts. And the idea behind that is that those always-on experts are always going to learn just shared level of base knowledge. And that basically allows the routed experts to learn much more specialized knowledge. So this was 16 billion parameters, but only 2.7 were activated, and it outperformed a 7 billion parameter model as well. So that was a big efficiency boost.
Do we want to just cover MoE just a little bit more?
Sure, yeah, sorry. So a mixture of experts basically is you take the standard, sorry, I don't have like a picture here to show it, but you basically take the standard transformer architecture. You have the attention layer, and then you have the feed-forward layer. You basically split the feed-forward layer into a whole bunch, maybe call it 16 or 32 experts, and they're all just feed-forward layers. And then you have another another little learned module that basically outputs probabilities over those feed-forward networks. And then what you do is you sample from that probability distribution, and you take the top K, so call it, if you have 32 experts, you take the top 4, and then you only actually feed the activations into those top 4 experts, and you get them back out, and you sort of do like it depends on the implementation, but usually do like a weighted sum over the outputs of those experts. And the idea behind that is that you can have like 32 experts and all the learned parameters that come with those, but you don't actually have to pay the computation cost to feed forward through all 32 experts for every token. You only need to feed forward through 4, or 8. So it's a big test time efficiency gain.
I have a quick question on that. Do the experts like talk with each other, or is it just like controlled by that feed forward initial root layer?
Yeah, usually it's just controlled by the router, and they have no interaction. So they basically took the mixture of experts technique that they were using with the shared always-on experts, and then they also brought in this thing called multi-head latent attention, which we'll talk about a lot more because that's like one of their biggest innovations. This V2 was 256 billion, 21 billion active, so when you ran it, you would only actually use the compute as if you were running only a 21 billion parameter model. So it was quite a bit quicker to run than a full 256B model, but the idea is that at least you get the learning power of 256 billion parameters. Trained on 8.1 trillion tokens, and yeah, used MOE and MLA. So we'll talk a lot more about MLA, but V3, this is what this talk is on. It's pretty much exactly the same architecture as V2. The difference is they add in a different objective. They add in actually a few different objectives here. And then they do a lot more with the data, and then they do a lot more advancements with actually how they train it and the engineering behind that. And I think that's what a lot of the news recently has been about, is their engineering efficiency gains. And also it caused, I looked it up, it was the largest single day US tech sell-off ever, including 2008, and 2001. So that was pretty crazy. So the DeepSeek specific MOE, I talked about this a bit in the past, but experts are not specialized enough. That's the knowledge redundancy problem that I was talking about. The solution is you basically cut the experts into a lot finer grained experts. So instead of having 32 experts, they went and did 256 experts with only 8 selected. And the idea is that if you have many, many more experts, they'll each learn a much more specific set of concepts than if you only had 32 and each of them had to learn quite a bit more. Then the expert redundancy, as I said, was solved with shared experts that are always on. So in that slide there, on the left-hand side, you see the ordinary mixture of experts equation. Really what you want to look at is the top level equation there. And you'll see that basically you're doing like this weighted sum over feed-forward networks. Each of those FFNs, that's an expert. And then on the right-hand side, the first equation, you see the DeepSeek one. And so you basically have the same piece as traditionally with the weighted sum, but then the first term in the equation there is the always activated experts. So that learns a lot of shared knowledge there. And then they basically, there's not a great way to test how much redundancy is in the experts. So what they did is they assumed that if each expert was more specialized and you were to run the network normally, but then you were to basically disable the top routed experts and force it to route to other experts, like the ones that it doesn't really prefer. If the experts were more specialized, that would hurt the performance more than if they were all learning sort of redundant information. And so what they did is they compared their MOE to G-Shard, which is another mixture of experts implementation. And they disabled the top routed experts, and they saw that theirs had a much larger loss once they disabled those. And so at least the assumption here is that that means that the experts are more specialized. So the MLA, multi-head latent attention, this was probably the biggest innovation that they had in the paper, at least in my opinion. The KV cache is, okay, I'll do a quick background on key value cache. So when you have attention, you basically take your sequence, you do projections into keys, queries, and values. And the queries, basically, you do some attention from the queries to the keys, and you get this attention matrix, and it tells you how much, for the next layer, how much to mix in other tokens from the previous layer. But the thing is, when you're doing inference, you're basically feeding the same sequence back into the model again and again and again. there's no reason to actually recompute the keys and the values because those never change. Those are from the prompt, you recomputed them last token. So what you do is you cache those, and that's called a key KV cache. And that's a big limitation on inference because on long contexts, everybody wants to feed in 1 million tokens, but for each of those 1 million tokens, you need to have a KV cache, and then when you're serving it on a GPU, you can run out of memory really quick. So this is a really large memory hog during inference. You want to limit this. So there's a couple techniques that they use to limit this. DeepSeek uses none of these, but these are traditional techniques. So on the left-hand side, you see the typical multi-head attention. You just have like one key, one value, one query for each head. But what if we were to have only one head, or only one key and only one value for each head, and we were to share them amongst all the queries? And then you basically get what's called multi-query attention there. That, if you have 32 heads, that makes your KV cache 1/32nd the size. So it really shrinks down, but it also is terrible for performance and accuracy. It never actually worked super well. So I don't believe anybody uses that anymore. Grouped query attention is sort of an interpolation between the two. So you don't have one set of queries and keys shared between keys and values shared between all the queries. You have n, where n is smaller than the number of queries. So in this illustration here, you basically have 1/2 of the number of heads, and that's how many keys and queries you have, and you share them. Each one gets shared to 2 queries. That also has performance hits, and it also doesn't save you that much memory. Like in that case, you only use 1/2 the memory.
Do you maybe you want to talk about what attention heads do in a transformer?
Sure, yeah. So all right, really briefly, I'll touch on basically the reason we do multi-head attention. So we could just do single-head attention, and it kind of works how I discussed previously. So you basically have a query vector, and you multiply it by every key vector in the sequence. You get out a whole bunch, you dot product it with every key vector in the sequence. You get out a bunch of attention scores, and then you do a weighted sum over the value vectors with those attention scores. And you get out one weighted sum value vector, and that's what you feed to the next layer. That would be single head attention. That people have done that in the past, but what they've pretty quickly gone to is saying, all right, instead of doing a big softmax over all those scores over the, once we do those dot products from query to all those keys, instead of doing one big softmax, what if we instead divide up the query into segments, say 8 segments, and then we did dot products with those, and then we had basically 8 separate probability distributions. And then we multiplied those probability distributions. We basically do 8 different weighted sums and then concatenate back into a vector of the original size. And that turns out that each head actually learns to attend to different things, and your layer is able to attend to many things at the same time. You don't need to just attend to one token from the past. So multi-head attention really is a really big performance boost. I don't know if that was clear or coherent or just rambling. Okay. So yeah, we want to reduce the KV cache size, but none of these options really work. But what multi-head latent attention does is a really interesting thing. So what if instead we compressed the vectors, the KV cache vectors? We're able to learn compression because we're dealing with neural networks here. We would only need to store these compressed vectors in the cache. And if that compression ratio is actually really good, then that can actually be a really huge savings. So the problem with that, though, and I didn't touch on rotary embeddings, but you can sort of picture rotary embeddings as rotating a vector in the vector space by a certain amount depending on the position. And the position of the token basically affects how much rotation you apply to the key, and in this case, it's just the key in the query. So that rotation basically happens before you end up doing the dot product operation that I talked about, which means that if it's dependent on location, and you then go and compress, you can't compress and then do the rotation. You basically have to do the rotation before you compress, and if you don't actually know the position of the token ahead of time, because the position changes as you add elements to the sequence at inference time, you basically can't compress. You have to redo the rotation before you compress at every turn, and so that negates the use of the compression. At least that's my understanding of the decoupled rope here. We will go into the equations here and kind of see how that works, but the end goal, the end outcome of MLA is that they got quite a bit better performance, quite a bit better modeling capacity, and they saved a ton on memory. I don't know the exact ratio, but they sort of lay out how much memory they use here. And so you have, you notice that N here is in the previous two, and N is the number of heads you have. We don't actually have that N factor anymore. And we just basically add in the dimensions of the hidden vector and the dimensions of the compressed vectors, and then you multiply that by the number of layers. I think it ended up being like 1/40th the size or something like that. It was like really a huge savings. But yeah, if we look at the actual equations here, what we see is the first equation, we basically have the hidden coming in, and we're sort of compressing it down into that C vector there on line 37. And then the next, what we do is we basically uncompress that into queries using a special matrix to do that. I'm still a little confused on why we end up compressing it and then immediately uncompressing it, because this is the queries, so this always happens just with the latest token. We're not saving any part here.
Does anyone want to add input on that if they know why that's being done?
Yeah, it's a bit confusing. But yeah, so then we get the query on line 38, and then what we do is we basically multiply it by, so this is the decoupled rope part. So we basically do the line 38 where we get part of the query, and then we take another part, and we basically like split the query in half. We take another part, and we multiply it by a different weight matrix, but then we do the rotation on that, and we only do it on that smaller vector. And so we don't need to actually rotate the entire thing. And then we basically concatenate the two. So only a part of that vector is rotated, and it turns out, I think that is enough positional information. Oh, right. I think you're right, yeah. So I think the compressed query in this case is shared amongst all the heads, and then you have to decompress it to get back to the original one-to-one head mapping. The keys and the values are kind of straightforward. So on line 41, we basically do this, we have this WDKV matrix here, and we multiply that by the hidden, and then we actually get the compressed key value vector. It's a single vector, not two. And we ended up saving that. So that's the one that gets cached. And we also cache on line 43 as well. But the blue things there are the ones that actually get saved in the cache. And so those are the pretty small compressed vectors. And then what we do is we take at inference time, when we actually want to use the compressed KVs, we take that and we multiply it on line 42 by WUK, which is a weight matrix, to decompress it into the full key. And then what we do is we also, sorry, not the full key, a part of the key. And then we take another part of that, we do the splitting operation again. We decompress the other part of the key, feed that through the rotation, and then we get out the other part of the key. And we also are caching that. And then once we have those two pieces, we can concatenate them, and we're back to our original key. The value is even simpler because we're not dealing with any rotation. So we're basically just decompressing that with a single weight matrix. We're taking the compressed key value vector, and then we're decompressing it, and we have our value. And then the rest of it works identical to attention, to standard attention. So we're doing our big dot product operations, and then we're doing a softmax over the resulting weight values, attention weights, and then we're doing a weighted sum over the values once we apply those attention weights. So does that make sense? That is a lot of math there. If anyone's got questions, let me know. But yeah, the output of this is that they actually compared it with the two other methods here, the grouped query and multi-query, and it ended up actually working better than both, even though it took a lot less space than either of them. So that results in them being able to serve a lot more users per GPU during inference. The other piece during training was basically they added in a loss that does multi-token prediction. I don't know if I've ever seen this in another LLM pre-training pass. So they basically take the output of the standard transformer. Normally, you get the hidden output of the transformer stack, and it's just this vector. And then you feed that through the de-embedding layer, which gets you a probability over tokens. And that's one token. What they do is they do that as well, and we see that all the way on the left here. That's the initial forward pass. And so we get out this token distribution. But what we do then is we sample a token, and then we have the new sequence with that added token. We feed that into a mini transformer. It's a one-layer transformer block called the multi-token prediction module. And then we also take the output weight of the original transformer pass, and we concatenate it with like the same vector, the output weight vector, with all of the embedded token vectors as well. And so we get like a sequence of vectors that is 2 times as wide as the original token vectors, and we have then a linear projection layer to bring that back down to the original embedding size, and then we feed that through to a normal single layer transformer block, and then through a shared de-embedding layer to get out another token. And notice we only actually fed one transformer block here to get a second token out. So we pay a very low cost to get these additional tokens out. And in this case, the transformer blocks are not shared. So I don't know exactly how many tokens they predict at once, but say they predict 5, there's basically 4 other trained single layer transformers that are just sort of trained to try to predict further and further out into the future. So that lets them basically train on 5 tokens for only slightly more than the cost of 1. And so they end up getting the same standard cross-entropy loss for each of these each of these predicted tokens. And then they add that into their loss. You see as the second equation there, that is the multi-token prediction loss. And so that just basically gives them more signal for each forward pass during training. And then they don't actually use this. In theory, they can use these because these predict multiple tokens per forward pass. It would be an inference boost. But they don't actually use them during inference. Once the training is done, they just throw them out. So yeah, that basically wraps up the training and algorithmic piece. And now I'm going to talk more about engineering. If anybody's got questions about algorithms, let me know. So this is like what all the news talked about and why NVIDIA stock crashed and why it was like such a big deal. And what sort of interested me is their engineering, because their engineers are like extremely good. So they basically use H800s because we have an embargo on H100s. And I know the rumor is that they secretly have H100s, but that's unsubstantiated. They have H800s. The main difference is that NVIDIA cut the memory bandwidth way down. And memory bandwidth is arguably more important than total number of flops. So basically total amount of compute on a GPU, because you need to get the weights into the compute units to actually operate on them. And that ends up usually being the limiting factor, and it certainly is the limiting factor with H800s. So how do we improve compute intensity? How do we end up needing more compute and less bandwidth? How can we trade compute for bandwidth, basically, is their question. One way, a way that a lot of people have used in the past is you just lower precision. Everybody trains in 16-bit floating point right now because it is stable enough to train. Every time people, at least as far as I know, most of the times when they use FP8, though, 8-bit floating point, the training ends up spiraling off and you get like not a number of values and it never actually works out. It's just too unstable. You need more precision to train. And these guys ended up figuring out how to put something like 90% of the weights in FP8. They had to be very careful where some of the network, they actually invented a custom floating point format. So it's a 12-bit format here just for the inputs to the mixture of experts layer. And then they did some fancy stuff. I think they used 12 or 16 bits for the accumulations inside each layer. And that allowed the errors to not grow too big. And they stored the optimizer state 16 bits. But yeah, and then the specific, what we see on the right there for people who are not familiar with low precision floating points is we basically see the representation of FP8, or at least the variant they used. So you can see the blue digit there is a sign bit, tells you if it's positive or negative. The orange bits there are the exponent, and then the greens are the mantissa. The exponent sort of defines the range, so the minimum and maximum values that this number can take. The mantissa defines the number of decimal points, so how precise within that range it is. I don't know the exact maximum number in this case, but it's not that big because there's only 5 exponent bits. Generally, this is good enough for inference, though. Inference doesn't have nearly the same tolerances to errors building up, but in training, you're running a bunch of passes. Errors that happened in the previous training step affect your current training step, so it's a lot more sensitive to buildup of precision errors. They obviously cannot fit the model in one GPU, so they end up using something called pipeline parallelism. And this is basically where you divide a model up into a whole bunch of GPUs here. And there's a lot of research on how to best utilize a bunch of GPUs to run a model. The most obvious way is like, okay, if you have 4 GPUs and 4 layers of a neural network, you run the first layer on the first GPU. Once that's done, you go to the second, run the second, third, fourth, et cetera, et cetera. But that's horrible because as soon as you're done running the first device, the first layer on the first GPU, and you go to the second one, now the first one shuts off. And then you go to the third one, the second one shuts off. So you have a lot of idle time. And so what this top left diagram is showing here is the top to bottom, the rows. Each row is a GPU, is a device. And then left to right is time steps. And so you're seeing basically the blue is a forward pass, the green is a backward pass, and anytime the boxes are gray there, the GPU is idle. And most of that image is gray, so you're wasting a whole lot of money with all those GPUs being idle. So no one really uses this. People have moved past this pretty rapidly. The next image, I think, is from GPipe. It's a Google paper, I believe, from 2016, something around there, where they reduce the amount of idle time by basically dividing the mini batch. You have a mini batch, say 64 elements. You divide the mini batch into micro batches. So say you divide a mini batch of 64 into 4 micro batches of 16 examples each. And then what you do is you run the first micro batch on the first GPU, and then once that's done, it goes to the second GPU. Once it goes to the second GPU, at the same time, you put the second micro batch on the first GPU, and then to the third, and you sort of have this pipeline then. So anytime the first GPU is freed up, you shove another micro batch into it. And then once you're done with your 4 micro batches, you don't have any more examples to shove in, so you basically have idle GPUs. That happens until you get the last micro batch out of the last GPU, the forward pass is done. Then the last GPU starts on the backward pass of that last, or of that first micro batch. And you do the exact same process, but in reverse. So you see on that image there, we basically have a big pipeline where you can sort of see this pattern of diagonal flowing upwards. That's the forward piece, and the exact same thing is mirrored going downwards for the backward piece. We have this middle area, though, where the devices are not running because we need to wait on the last GPU to do the last forward pass on the last micro batch. And that's called a bubble, and that is what really kills a lot of training efficiency, because all your devices in that bubble need to be idle except for one. So it's a pretty poor utilization of hardware. So there's been a ton of work trying to figure out how to eliminate that bubble, or at least reduce it. Nobody can fully eliminate it, but so what we have here is something called, I don't remember what this is called, but it's from Microsoft from, I want to say 2018 or 2019. It's a different scheduling scheme where we basically start doing with the same pattern as before. We start, the first micro batch across all the devices. And then once we have that done, the last device actually immediately starts the backward pass of the micro batch, the first micro batch, because it's ready to go. And then you sort of hold off on the forward passes. If there are any backward passes available, you immediately do those backward passes. They take precedent. Oftentimes, the backward passes take longer as well. But basically, yeah. So this results in that pattern you see there. So the first, you immediately go to the backward pass of the first micro batch and then finish up the forward pass of the second afterwards. So you wind up with a lot less of a bubble in this case. This shows like a full run of a full mini batch. And then right at the end, you have the optimizer step, and then you go on to the next one. So there's quite a bit less wasted time here. I believe most training runs have ran a similar methodology to this up until last year, I want to say, or 2 years ago when they started publishing more complicated schemes, because it does get more complicated. This is what DeepSeek did. They kind of went nuts with this. They have essentially the same, a very similar scheme to this last pattern here, except they do it bidirectionally. So they start at both the last device and the first device simultaneously. And they do a very, sort of similar scheme where you sort of prioritize backward passes over forward passes, but they do this in a very bidirectional pattern, and you can sort of see the top and the bottom halves are also mirrored there. And what they also did, a clever thing, is when you're doing the backward pass, you're basically taking the derivative with respect to both the weights and the inputs. And we always have seen that as the same operation, but in fact, you don't need to see that as the same operation. You can get the derivative with respect to the inputs without paying the cost of getting the derivative with respect to the weights. And you only need the derivative with respect to the inputs to flow the gradients to the next layer, to one layer back. And that's what's holding a GPU from doing the next backward pass, is it's waiting on the derivative with respect to its outputs, basically, as they flow back in. So you only actually need the derivative with respect to the weights to do the final gradient update. And so basically what we see in this diagram is orange is the forward pass, green is the backward pass, but only with respect to inputs. And you see that those are prioritized pretty early on. And then blue is backward pass with respect to weights. And that's sort of loaded only at the back, only on the back end there when there's nothing else to do. Of course, you have to get all those derivatives before you end up doing the full gradient step, but those are lower priority because they're not gating any devices. So there's not a whole lot of info on this other very interesting part, but this is where they specialize pieces of the GPU just for communication. I know this popped up in a few news articles. They didn't talk too much about this in the paper, but basically what I surmise, what I've gathered from what they have said, is they use this thing called PTX. So just a quick background on GPUs. GPUs are programmed in a language called CUDA. It's a variant of C, or C++, sorry. And basically, that CUDA C++, or GPU programmers write that by hand. That gets taken by the NVIDIA CUDA compiler, and it's compiled into something called PTX. PTX is not assembly, it's not machine code, but it's assembly-like. and you can sort of think of it more as like Java bytecode. It's like a higher level assembly that ends up getting interpreted differently depending on which GPU you're running on. And so then the actual like GPU driver ends up converting it right when you're going to run it, converting it to an even lower representation that I don't think NVIDIA lets anybody actually write. But you can do a whole lot if you write PTX instead of CUDA because you don't rely on the NVIDIA compiler. So what they've done is, in the same way you can write inline assembly inside of a program, they have written inline PTX to sort of gate out 20 streaming multiprocessors, which are little cores on the GPU. They basically gate those out and then say those are only going to be used for communication operations, and then the rest can be used for compute. And the reason they do those also is because of bandwidth. They want to limit the amount of communication they need to do. One way to limit that is to do operations in transit. So if you have to gather, basically, if you have to accumulate, say, 10 numbers from 10 different GPUs, what's the fastest way to do that? Well, what you end up doing, instead of sending all 10 numbers to one GPU and then doing 10 additions, what you can do is you can send 5 of them to 5 other GPUs, do 5 additions there, and then send, so you sort of cut in half the number of numbers you have, and then do that again and again and again until you get down to a single GPU. And that's called, I don't know what that's called, operation in transit, I guess. You're basically doing these accumulates as the data is flowing in. And so that's what these 20 cores are held to do, and it reduces the amount of bandwidth they actually need. And then sort of as results, what's the results of all this complexity? They ended up actually getting state-of-the-art on a few benchmarks here, and they came very close to state-of-the-art on many other ones. So on all of these, they only lose on like 2 of them, I think the ones that they published, and they only lose to like the latest, Claude 3.5 Sonnet, latest at the time, and that's obviously closed source. And then the real headline figure here is how many GPU hours they used. So they basically spent 2.6 million H100 or H800 hours. They estimated that the GPU cost per hour was like $2 or something. And they ended up at a total training cost of $5.3 million, which is kind of insane because it's, everybody assumes that it cost GPT-4 something like 100 million or 110 million to train. So there's quite a bit of a efficiency gain here. Obviously, DeepSeek didn't even pay this $5.3 million though, because they have their own devices. They don't need to rent them off the public cloud. So it cost them even less. And then they also did, I didn't touch on this very much because, well, it wasn't a huge part of the paper, but they also did some post-training. So they did some instruction fine-tuning, and then I think they did some direct policy optimization as well to basically get it to follow instructions a lot better. And they also did a little context extension pass, so they only trained with a context length of 32,000 tokens. Obviously, people want to feed in larger prompts, though, so they do a context extension training pass where they feed in much larger sequences after they've done the main training, and this they only do for 119,000 GPU hours, which sounds like a lot, but in the context of everything, it's kind of small. And then they did, the instruction fine-tuning is like a very, very small piece. They don't list it here, but R1, which was like the big reasoning model that they came out with based on this one, probably also was a pretty small amount of training as well, so that probably doesn't raise the price tag very much. But yeah, that is DeepSeek v3. That is more or less the whole thing. If anybody's got questions.
Any remaining questions from the audience? Okay.
Can you say a little bit more about, it was a minute ago, whenever you were saying that you take the token outputs from the transformer, or like the token probabilities, and then you feed that into a one-layer transformer?
Yep.
Could you go over that one more time?
Sure. So you have a standard transformer stack, right? And you get the hidden vector after the last layer of the transformer out. And then all you have to do is you feed that into like a head, like a feed-forward layer, and you get out the token probability as normal. what you do is you then have this new sequence of tokens. You sample from that token probability, you get the new sequence of tokens. You feed that new sequence of tokens, you re-embed it, and you feed it back into a little transformer. But instead of that little transformer just being a normal, ordinary transformer, because that would make too much sense, they take the hidden vector output from the original forward pass after the last transformer layer, and they concatenate that with the embedding vector of the incoming re-embedded sequence. And now your embedding vectors are 2 times as wide. And then what they do is they take that and they feed that through a projection layer to project it back down to the normal embedding size. Now they feed that through a 1-layer transformer, get out a new hidden vector. They put that through the same head, the same shared language model head, to get to a token distribution. And now that's your second token. And you do the same process again with a different transformer block and a different feed-forward projection layer, but the same last token projection. Basically, everything on this graph that is green is shared, and everything that's yellow is not shared between the heads, the multi-token prediction heads. And so basically what this ends up being is, if you want to predict 4 tokens at a time, you have to have 3 other multi-token prediction modules, so you have to train 3 other transformer layers. But you get to predict 4 tokens at a time, so there is a benefit. And then I guess, because they're all connected through a hidden vector, the gradients can flow back through to the original transformer. And so you get 4 times the signal in that case. They didn't really talk too much about this, though, and how it benefited. They did a little bit of an ablation, and it did help a little bit, but they ended up throwing this out, which I'm kind of surprised about, after they finished training, so that was a bit shocking. Sure.
So I think I don't really like this figure, how the DeepSeek people have made it, because actually, if you go into look at the Hugging-based code, they really only have one of the modules. So it's kind of they in the diagram they show okay, you have module 1, module 2, module 3, module n, but really it's only one module. So you're basically just taking your hidden states from your main model, right, and passing that through this MCP module,
Mm-hmm.
and you basically shift the, as you mentioned, shift the inputs, and then backpropagate with that one model. And they actually had, I think, way down, I think it's a very small section in the paper where they actually mention that you can actually use this MTP module as
Right.
as a speculator.
Right.
But you're right, they do throw it away after training.
Yeah.
I don't think they use it in their instruction fine-tuning phase or.
Right. Right.
So I think then the number that they quoted, somewhere 85 to 90%, is the acceptance rate, which is about 1.8x speed up.
Yeah, totally. Wow. So basically, there's not multiple MTP modules, it's just one with shared weights. Okay, makes sense. Any other questions?
So actually, back on the part where you're talking about the engineering side, do you have you seen any do you get any inclination that they're gonna do any custom hardware stuff, or build their own type ASIC type? Similar to how Google built their TPU.
I don't think they're big enough yet. They're not making a whole lot of money. So I hear they're not making a whole lot of money on their inference because their prices are so low. So I don't know if they're going to have the financial backing to do that. In my experience, it costs quite a bit to tape out your own accelerator. But I do know that Xiaomi is making an accelerator, and the Chinese government obviously is very interested in having a fully domestically sourced accelerator. So I wouldn't doubt, I know they're trialing inference on the Xiaomi accelerators as well. So if you go on there DeepSeek.com and you try out their inference, there's a very good chance that that'll run on a Xiaomi GPU. But the hardware constraints for actually training are a lot stricter. So I would be very surprised if they moved off NVIDIA for training, at least for their next models, the next year or two.
Okay, yeah, that makes sense. I was just kind of curious, like, why you think like they could have done some like FPGA stuff or something too, right? Like there are some companies that do some FPGA stuff, but there's like GraphCore, there's like other models beyond pipelining that are like a little bit potentially more advanced, but I don't know if they like looked into anything like that, like, or they just tried to mess around with the GPU stuff. Because I mean, the GPU thing was really cool too, but
Yeah, it's
yeah,
very non-trivial to get a custom accelerator to work
sure,
as well as a GPU. I'm at least, I've done a little messing around with the TPUs. They're extremely well designed, but aside from the TPUs, almost every custom accelerator is very difficult to work with. And if you actually look at a GPU, it's like sort of like, where's the waste on a GPU? TPU, sure, they get rid of a lot of control logic. If you look at a GPU that, like, in terms of floor space actually spent on control logic circuitry, it's like 4%, 5%. You're not gonna really save a whole lot ditching that, and your accelerator is gonna become a lot less flexible for doing that. So, not to say that they can't, and I'd love to see some more like systolic array-based accelerators or something like that, but I'm pessimistic. This one or the next one? Okay. Every layer of the transformer, yeah, every attention layer has to have its own KV cache. No. So these are heads within a single token of the attention layer. So you have, 1,000 tokens in your sequence that you're training on. Within each token, you may have 32 heads. And that's what this is showing. So this is like the blues are the queries here. You have 32 different queries, and you want to attend based on each of those 32 different queries. And ordinarily, in normal multi-head attention, there are 32 sets of keys and values to attend to as well. And that's sort of what this illustration is showing. If you were to use multi-query attention, you still have 32 queries, but you only have one set of keys and values. And those are shared across all the queries. And then grouped query is a interpolation. So then what they did is, it's multi-head still, but basically what they did is, yeah, they compressed it into a single vector that represents the compressed form of both keys and values. And then they decompress them into their own keys and their own values when they actually want to use it. And that is extra compute, by the way. This is more computationally expensive than just using standard multi-head attention, but again, they are bandwidth limited, not flops limited. So they're trading compute for memory bandwidth.
So here, when it's being compressed down from H to C and back up from C to the K or Q, these are both linear projections, right? So you're projecting down to a lower rank.
Right.
And then back up. But I mean, why go back up at all? Isn't it just, I mean, if it's still linear, then you're not going to get any advantage by going to a higher dimension.
That's a good question. I know there's a reason, but I'm trying to remember it right now. Yeah, you're basically saying, like, why not just do the whole attention calculation in compressed space?
Yeah.
I don't know, but there is a good reason. I just don't know it. Good question.
query to like that embedding dimension times the number of heads, which is 12, and then you split the query like across you know, the number of heads you have. So like 12 in that example. So I mean, I think that's why. That's fair.
I think that does make sense, yeah. Right. Okay. Anyone else? All right.
All right, please give him a round of applause. All right, so you're welcome to stay here for about 43 minutes. And after that, you can still keep networking past those glass walls. If you haven't already, please join as a member on Meetup so that you're able to get a nice little email reminder every time we do these. We typically do these on the first Tuesday of every month. So I'll leave this up for a moment. And we have an announcement. So there's an event going on later this month in April, and it will be here at Capital Factory. So David's gonna be the one organizing the event, so I'll let him speak.
Hey guys, so this is coming up in just 3 weeks. We're doing a whole Agent Builders event here the 23rd and 24th. So there's only about 100 spots. We're bringing people from all over the US to come and present what they've been building on the agent side and help people that want to integrate open source and decentralized inference for their agents and sort of integrate all of those tools. So definitely scan the QR code and register. There's only about 100 slots and it's about half filled already. So check that out. If you can't get into the main event, I'd also recommend the Decentralized AI Happy Hour. We're gonna have that on the 22nd as a kickoff event right before the demo days. So feel free to register that. We'll have more capacity there as well. So if you're interested in open source models, if you're building agents on them, if you're interested in how to access decentralized low-cost inference of those open source models, it'd be a great opportunity. A lot of the top builders from around the US are converging. Sort of a cool opportunity because there's no consensus this year in Austin because of the renovations of the convention center. They're up in Toronto this year. So we're basically putting together an entire decentralized AI week here in Austin, and this is like the kickoff of that week. As you can see, most of the major protocols from Morpheus, Venice, Base, Akash, a lot of those groups are based here in Austin, but those are the big names in decentralized AI, are holding this whole series of events from the 22nd all the way to the 26th. So if you're in town that week, highly recommend plugging into this community because there's billions of dollars of capital that's gone into building these protocols, and it's really scaled up amazingly the last few years. So again, here's the QR code for the Luma for the demo days. Again, the structure is we'll do the kickoff on the 22nd. The demo day on the 23rd will mostly be the builders presenting what they've created and people showing off the tech stack for how you can connect agents, compute, capital tools for open source builders. And then finally on the 24th, it'll be more of like a workshop where you'll be able to go in depth with all the engineers behind the different protocols and get hands-on, one-on-one with them. So anyway, feel free to register, and big thanks to Ruckchuck as always for organizing. Thanks, guys.
So before we break for networking, out of curiosity, who here is using any agent at all? Like DeepSeek, sorry, not DeepSeek, Deep Research would count in my opinion. Is anyone using Deep Research? Okay, who was using any agents last year at all? No? Okay. Yeah, so we're pretty early in this. I think agents are gonna transform how, I think all SaaS applications are gonna turn into agents. And so there's a lot of interesting challenges there on how you do like payments, how you do compute, scheduling, and resourcing with all the constraints of the industry right now. So I think it's a really cool chance here to talk to people who are building in the real world with agents, and yeah, it'd be good. So yeah, please hang around until 8:45. And again, we're Austin Deep Learning. There's a lot of great people here. I always have really amazing conversations in this room, once we're going with the talks. And we're always looking for more speakers as well. So you don't have to be an author on any of these papers, but if you have any kind of insight you want to share. These do get recorded, so if you want to use that as part of your portfolio, you're welcome to do that as well. We're always looking for researchers. A lot of people who give the talks here, are just regular attendees like you guys who want to present something. So yeah, please break out and network and mingle and have a great time. Thanks.
I'm really interested in the token thing, just because like it seems like sharing the MLP activation layer is right before not decryption, it's the only word coming to mind. Decoder. Yeah. So like if they're sharing the MLP layer, that's a ton of information, right? That's taking all of the information that was there and that's giving a much deeper thing because in my head what you do whenever you actually create whenever you just create the probability of the tokens, you are storing away so much of that information, right? Like you're just getting rid of it. So whenever you take that and then you try to get it, isn't that a compression layer in itself? Like could you think of that as like bottleneck specifically, and then you're training on that bottleneck? So instead of doing the classical thing of token prediction, now you have it to where you have to compress more information in those tokens than before. So you're cramming more information in and then you're cutting it off, which I'm gonna be honest, I don't know why that works.
Well, I think it's like, I think it probably has to, yeah, and I have to look into that more, but the gist of it that I get is like, the reason, and are you talking specifically about like why it's going away information? Or like, yeah, so basically, it's kind of like the same concept of like attention, right? So like, basically, you have a bunch of information. Some of it's relevant and some of it isn't. But it's hard to know what's relevant and what's not until you go and do the training. So that's why you collect like a lot of information.
Oh, so you're saying that like
and then you just get
an attenuation, like a
exactly
on the important information, so there's one without it. Okay.
Exactly. Because like that's like the whole goal of like compression, right? It's like what's like the most interesting information in there. It's information theory, right? So it's like basically it's like not all of it's interesting, but it's like define what's interesting. You kind of have to like do this like large training thing, and then you have to get what's interesting, and then you like take the stuff that's not interesting, and you keep the stuff that is interesting, and you throw away the stuff that's like not interesting.
And this adds to work against like your extend out force. Yeah, but you make sure that you're focusing on what is actually going to last.
Exactly.
Okay, yeah, that makes a lot more sense.
Yeah, exactly.
Yeah, that's a lot.
Yeah, it's kind of fascinating. I think it's cool. I mean that's kind of like that's like a lot of the fundamental idea of like transformers. Because like as you're doing like a lot of coder stuff, it is exactly so like when you said decryption and you mix it with decoding, it's some concept, right? Because it's like and those are kind of like
I think of it so much more basic, where I really think of the attention layer itself as just taking information that's already there, then moving it around. All you're doing is you're taking your fish, you're chopping up your fish into different pieces, and you're giving it to the chef. Which the MLP layer, the MLP layer is going to do the chef. The chefs are going to take these things and prepare it in such a way where they cook it or do whatever to bring it into the dish. It's all about taking the information and then moving it where it needs to go and doing the minimal amount of operations. In my head, the attention mechanism, or not the transformer mechanism, doesn't want to do much of anything. It wants it to be as lazy as possible. The less you do, the more targeted you are.
That's like one way to look at it. I think that's like one way to look at it. I think that like it's also just like I mean that's why like the whole goal is like attention is all you need because it's like this whole concept of basically saying like where do you put your attention on, right? Because it's like that's what that's why you like mention hallucinations, right? Because it's like hallucinations are basically just like irrelevant that like basically the way that I think about it, it's like looking for it's a certain problem. It's like looking for information that's relevant to the area and fragments information. But whenever you have tons of information, then you can kind of run into these contradictions, and it doesn't know where to really place its attention. So that's why you can kind of see why sometimes they'll hallucinate. Because like sometimes it's like misinformation, right? But that's like still the same mess up in my opinion. Because it's like you're trying to get some answer that's qualified for the end user. However, it's a confusion problem. Like it's getting confused. It's like, okay, is this really what the user wanted, or is this really true in some context, right? So it's like kind of like getting kind of confused. And that's like the whole idea of multi-head attention, even though I think it still needs to like improve. And that's why like you have like GPTs and GPT-2 and GPT-3 kind of make it better, and like with more data, for example, or you can make it more specialized, right? So you're seeing like agents kind of when they're like more specialized in one area, you kind of mitigate that and like hallucinations in some way. Or you know, I mean, you can think of like a lot of incorrect models that gives you one, like you know, it's like a rudimentary model of that. But the whole point is that yeah, you want to get better at like optimizing that hours or like that, you know, those kind of things. I think that's like interesting. It's like I think it's interesting. For me, like the idea is like the way that they're doing it with compression. And I kind of wonder what the compression mechanism is, because I guess they're using like the multi-head thing, but then they're like doing some compression thing that was kind of, I think I have to like dig deeper to better understand that, because that's what we talked about, I feel like, in a few other ideas, which is like this idea of like large concept models, or if you saw DeepSeek, if you remember DeepSeek R1, which is like chain of thought reasoning, right? So basically, like, you're kind of doing this thing where you're kind of, you know, taking like a batches of data rather than just words, and then that's your almost form of like compression. Versus, I don't know exactly what this is doing. I know it's doing multi-head, but it's like the compression mechanism is still like a little bit unclear, but maybe you have some better insights on that compression mechanism.